Hey guys, so in this video we're going to talk about what happens when you have multiple forces producing multiple torques on the same object. In other words, trying to get the object to spin in different directions. Let's check it out. So the first thing we need to talk about is the sign of torque. Okay, you might remember that with different forces, if you have a force going in different directions, like the positive x-axis, the negative x-axis, we use signs to indicate direction. Same thing happens with torques. But the direction depends on which way you're trying to spin something. All right, so if you're trying to spin something in the clockwise direction, which is the direction of the clock, it's negative, and counterclockwise is positive. Now, there's two ways that you can remember this. The reason counterclockwise is positive is because it follows the unit circle, right? The unit circle spins this way. It starts at 0 degrees over here, and it grows in that direction. Another way you can think about this is that the clock, the direction of the clock, is backwards. Clock is backwards. Okay? Those are two ways that you can remember the direction. This is the standard direction for rotation, so you should remember that. Now, what happens if you have multiple torques? If you have multiple torques, we can calculate the net torque. The net torque is the resultant torque. It's one torque that represents a combination of all of them, okay? And the net torque is simply the addition of the individual torques. So if you have two torques, it would look like simply torque 1 plus torque 2. Now, the big difference between forces and torques is that forces are vectors. They have a direction, a theta. They can be pointing in different directions. A torque is the result of a force, and a torque is a twist that's either clockwise or counterclockwise. That's not really a direction in the same way that a force can point in an infinite number of angles. This is just really two options. It's either going to the right or going to the left, or just going clockwise or going counterclockwise. It's not a direction in terms of theta, so there is no theta because they are scalars, not vectors. They just have an orientation that could be either positive or negative. Okay, so we're going to use simple additions and not vector additions to find torque. Remember, for forces, if you push this way with a 3 and this way with a 4, the net force is not 7, the net force is 5 because this is vector addition. With torques, if you have a torque of 3 and a torque of 4, the answer is always 7 because it's simple addition, not vector addition. Forces are vectors, torques are scalar. Let's do a quick example here. So I have two forces acting on the same door. The door is 3 meters long. It says force 1 acts on the center of the door. So this is the middle right here. So I'm going to say that this is 1.5, half of the length. And this is 1.5, the other half of the length. It says F2 is directed at 30 degrees above the x-axis. So it looks like this. And we want to know what is the net torque. And we also want to use signs, positive or negative, to indicate whether they're clockwise or counterclockwise, the direction, the orientation of the torques. Okay, the direction of the spin, I should say. All right, so what we're going to do is we're going to do torque 1 plus torque 2. There are two forces, therefore there could be as many as two torques. I want to remind you that a force may give you a torque. So if you have two forces, you could have two torques. You could have 1, you could have 0, but you can't have 3. Okay, so the maximum amount of torques you can have is the number of forces you have, 2. So we're going to do that. I'm going to expand each one of these guys. The definition of a torque is Fr sine of theta. So this is going to be F1 R1 sine of theta 1. I'm going to leave a little space here for us to indicate whether that torque is positive or negative. And then I'm going to do the same thing here, F2 R2 sine of theta 2. Now remember, to solve torque problems, there's 3 steps are you have to draw your R vector, you have to figure out your theta, and then finally you plug it into the torque equation. So let's do that first. Let's write the R vector. Let's draw the R vector for each one of these guys. What's R1 and what's R2? R is a vector, an arrow from the axis of rotation to the point where the force is applied. So R1 is from the axis over here to the point where the force is applied, R1. R2 is from here all the way to the end. This is R2 over here. So R1 is 1.5 and R2 is 3 meters. So we got those two guys figured out. Now, how do we know which way it moves? we're going to use the r vector to figure out whether they are, whether these individual torques are positive or negative, okay? And I want you to think of, here's the door, which is my r vector is happening along the door. And I want you to think of what would happen if you pull on the door or on your arm in these directions. So F1 is pointing down this way, right here, F1 pointing down, okay? So what you have, imagine if you're pulling on your arm like this, right? Or I can pull my thumb down like this. This would spin in this direction, okay? This would spin in this direction. So I can say that F1 is trying to get this thing to have a torque in this direction. I'm going to call this torque 1, okay? Now, let's put the bar back here, the door. What if you're pulling this way, F2, then you can think about it this way or just pull a finger at an angle, right? If you pull it this way, it's going to try to cause it to spin like this, right? Even though it's not 90 degrees, it's at an angle, it's still going to try to do it this way. And that's because it's basically, if you are above this line here, you're going to do that. And if you are any tiny bit below this line, you're going to cause it to do this way. You're going to cause rotation to go that way. So what you do is you extend your r vector, and if you're on top of it, you're going to go like that. If you're pulling sort of below it, you're going to go like this. Okay? So torque 2 is in this direction. Now, what signs are these? Well, this is going in a clockwise direction, T1. So T1 is negative, and T2 is going in a counterclockwise in the direction of a unit circle. So it is going to be positive. Okay? So this guy is negative, this guy is positive. Let's put those signs here. Torque 1 is negative, torque 2 is positive. The rest is what we've been doing so far, which is plugging in these numbers. So negative, the forces are both 50. The distance for R1 right here, 1.5. Sine of theta. The angle between R1 is the blue line in this one. So R1 and F1, the angle here is 90 degrees, easy. This guy is positive, so 50. R2 is the entire length of the door, so it's 3. Okay, and sine of, now I have to make sure this is the correct angle. So let's be careful here. I'm going to redraw R, then I'm going to redraw F. Okay, remember, one of the things you can do, you want them to be either all joining at the same point or exiting the same point. You basically want to make this easier for you to see. So there's a few ways you could do this. I think the easiest one is just to move this r vector up like this. And then you can see that this is in fact the angle you want, which is the angle that's given. So in this case, the angle given to you was the angle you're supposed to use. But remember, a lot of the times you're not supposed to use, the angle you're given is not the one you're supposed to use. Okay, so I have to be careful. Here it just worked out that way, so that's nice. Sine of 90 is 1, and sine of 30 is 0.5. Okay, so this is going to be negative 75, plus 75. So this is interesting. They both added up to 0. What does that mean? Well, if they both added up to 0, it means that they perfectly cancel each other out, and you actually have no rotation at all. So the net torque here, the sum of all torques, which is the same thing as net torque, is 0. And what that means, we'll talk more about that later, is that you have rotational equilibrium. The two forces, the two torques are canceling, so the object actually doesn't spin at all. We'll talk about that a little bit later, but that's it for this one. Cool, let me know if you have any questions, and let's keep going.